Okay, before we can use shaders, we need to understand how they work. So let me take you through a short presentation in this lecture so that we can gain a basic understanding of how the GPU works. The GPU is the graphics processing unit, which is the thing that's in your computer that's rendering graphics to the screen. So it turns out, for this rendering graphics to the screen to happen, a lot of computation needs to happen. So in a typical 3D game these days, you have detailed 3D models, you have lighting that's happening in real time, shadows being calculated, and all sorts of different visual effects going on at the same time. So all of this amounts to just a ton of 3D math, matrix calculations, all sorts of stuff that needs to happen. And all of this calculations, they need to result in a color for each pixel that's on your monitor. If you think about it, this makes sense, because the player sees the screen, and the screen is simply a 2D array of pixels. So the result of all the graphics is just a color for each one of those pixels. So all the 3D math, all the matrix multiplications happening behind the scenes, they all result in a 2D array of colors for each pixel, basically. If you have a 1080p monitor, which would be 1920 pixels wide and 1080 pixels high, then you have just over 2 million pixels. And 2 million sounds a lot, but if you think how many frames per second games usually run at, the number gets even larger. So a typical game these days runs at 60 times per second, and it can go up to 120 times per second. So each one of these 2 million pixels need to be calculated 60 or up to 120 times per second. So we're talking about billions of computations here every second. So this many calculations, this many computations is actually a difficult task for the CPU, which is the central processing unit, the thing that's running the game and the operating system basically. And the reason is the CPU likes to do things sequentially, and that means one after the other. So if you give billions and billions of operations to the CPU, it simply can't handle it because it's trying to go through them one by one. So calculate the first pixel, the second one, third one, fourth one, and there's just so many of these computations that needs to be done, the CPU can't keep up. But don't get me wrong, it's not because the CPU isn't powerful enough to make these calculations. In fact, each one of these pixel calculations is very simple. The problem here is the number of them. The CPU can take care of a single computation very easily. It just simply can't do them all because it's trying to do them one after the other. And to fix this problem, the GPU was made. Like I said, the GPU stands for Graphics Processing Unit. It's very specialized just to render computer graphics. I mean, the name literally has graphics inside of it. But these days, they're used for different purposes as well, but the original intent was definitely for graphics. And the way it solves this problem is by having thousands of cores, so that it can do many computations at the same time. This is also called parallel computing, because it's doing all these computations at the same time in parallel. So a typical CPU these days might have 8 cores, and you can see this in comparison to the GPU's thousands of cores. So it's because of these cores, the GPU can crunch through all of those pixel calculations, and it can handle the problem the CPU couldn't. Okay, so now that we understand what the GPU does, basically, we can start talking about shaders. A shader is simply a program that runs on the cores of a GPU. Shaders are written in shading languages, which are special languages adapted for programming shaders. So they have special features that make it easy to write programs for the GPU. And Godot has its own shading language that we're going to learn in this course, and it makes things very easy for us compared to other shading languages, which is a big bonus of using Godot. So that's what a shader is. Very simple, it's just a program. We have different types of shaders that run on different steps of the graphics pipeline. And the most important ones are the vertex and fragment shaders. So let's back up a bit. The graphics pipeline. What is the graphics pipeline? It's this. So remember when I told you that the GPU has to do a bunch of computations in order to determine the final color of a pixel. That whole process is called the graphics pipeline. So this top part here is the start of the pipeline, and this bottom part here is the end of the pipeline. And at the end, we have the frame buffer, which is an array that holds all the colors for the pixels on the screen. So it's the final result of the graphics calculations, the final result of the graphics pipeline. At the start here, we have the vertex buffer, which is given to the GPU by the CPU, and this holds the vertices. And the vertices are basically points in space that the GPU use to draw graphics. So as you can see here, we have 3 vertices, 0, 1, and 2. The GPU uses these to draw a triangle. The next step here is the vertex shader, and the vertex shader lets you manipulate these vertices. So you can use the vertex shader to change the position and other properties of these vertices. Then we have a bunch of other steps until we hit rasterization, which is also very important. Rasterization basically takes all the 3D geometry we have and turns them into a 2D grid of pixels so that we can, show it to the player, show it on the monitor. But these pixels don't have any color. That's why in the next step, the fragment shader assigns a color to each one of these pixels. And this is also something that we can control by writing a fragment shader. And after the fragment shader, we basically have the finished frame buffer that holds all the final colors for each one of the pixels on the monitor, on the screen. So that's roughly how the graphics pipeline works. Of course, I'm massively simplifying it. Understanding how this works is kind of outside the scope of the course, but if you want to learn more about it, at the end of this video, I'm gonna show you a resource that you can use. Okay, so that's the graphics pipeline. And like I said, the most important part here for us is going to be the vertex shader and the fragment shader. In this course, we're going to learn how to write these types of shaders. Because they're very important, let's talk a little bit more about them. First of all, vertex shaders. The vertex shader is run once for each vertex. So what is a vertex though? I did kind of explain it just now, but in order to understand it, you need to understand how 3D models work. 3D models are made out of triangles. And that's simply because the GPU likes to draw things with triangles. It's very fast at drawing with triangles compared to other types of shapes. And because of that, 3D modeling software usually works with triangles. And a vertex is simply the corner of the triangle where 2 edges meet. That's one explanation. You could also think of it as a point in space, which I think is a simpler explanation. If you take a look at this graphic here, it's going to be very clear. At the left side here, we have the vertices, and like I said, these are points in space. We can connect these points in space in order to get triangles, and then we can assemble the triangles to get the final 3D shape or model. So that's what a vertex is. It's simply a point in space that the GPU uses to draw triangles. And the vertex shader is run for each one of these vertices. So here we have 10 vertices. The GPU is going to run the vertex shader on each one of these. So it's going to run it on this one, this one, this one, this one, this one, this one. You get the idea. And inside of the vertex shader, we can manipulate these vertices and do all sorts of cool tricks with them, as you'll soon see in the course. So that's what the vertex shader is. The fragment shader is similar. It also runs once for each fragment this time, instead of vertex. And what's a fragment? You could think of a fragment as a pixel, even though they're not exactly the same, but for the most part, you can think of it as a pixel and you'll be fine. So once we get to the fragment shader, this is after rasterization, so now we're working with pixels instead of vertices. And the fragment shader is used to compute a color for each one of these pixels. So here we have an image and it's very low resolution so that we can see each individual pixel. The GPU is going to run the fragment shader on each one of these pixels. And the fragment shader is going to give a color. So for example, at the top left, the GPU is going to start running the shader. For the first one, the fragment shader is going to say this needs to be white. The next one also needs to be white. This also needs to be white. It's going to run through all of these pixels and give a color to each one of them, resulting in this final image. And the way the fragment shader does that, you can control, which is the cool part. So you can write different shaders that create different types of visual effects. Fragment shaders are extremely cool. They're basically limitless in what you can do with them. I love them, and I'm sure you're gonna love them too after you take this course. Okay, so some final words. So because of the parallel nature of the GPU, the way a shader processes information is not the same a typical program processes information. The shader code runs in isolation, on each vertex for a vertex shader or on each fragment for a fragment shader. This means you can't store data between frames. So each shader is basically memoryless. It doesn't have any memory. It runs, it does its thing, and it's over. The next time it runs, it doesn't remember what it did, basically. It's also kind of blind, so it can't really see other shaders running. It can only see its own self. So as a result of this, when working with shaders, you need to think differently compared to what you're used to making games in Godot. You always need to think, the code I'm gonna write is going to get executed in bulk in thousands of cores. And I know that sounds complicated, and if it doesn't make sense yet, don't worry, because that's why you're taking this course. In this course, you're gonna learn all about how to do shaders. So, if it doesn't click yet, don't worry, it's not supposed to. Okay, so finally, there's a video by Branch Education called How Do Video Game Graphics Work? It's a 20-minute long animation. It's excellent. If you want to understand how the graphics pipeline works better, definitely take a look at this. And with that being said, we're going to conclude this presentation. It's been a little longer than I expected it to be, but hopefully it was useful for you. Let's not waste time and continue with the next lecture.